Chapter 6, Enums and Pattern Matching. In this chapter, we'll look at enumerations, also referred to as enums. Enums allow you to define a type of enumeration by enumerating its possible variants. First, we'll define and use an enum to show you how an enum and encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that value can be either something or nothing. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how the if-let construct is, how the if-let construct is another convenient and concise idiom available to you to handle enums in your code. Enums are a feature in many languages, but their capabilities differ in each language. Rust enums are most similar to algebraic data type in functional languages such as F#, OCaml, and Haskell. Defining an enum. Let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work an IP address. Currently, two major standards are used for IP addresses, version 4 and version 6. These are the only possibilities for an IP address that our program will come across, and we can enumerate all possible variants, which is where enumeration gets its name. Any IP address can either be a version of 4 or a version of 6 address, but not both at the same time. That property of IP address makes the enum data structure appropriate. Because enum values can only be one of its variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. We can express this concept in code by defining an IP address kind enumeration and listing the possible kinds of IP address can be, v4 and v6. These are variants of the enum. IP address kind is now a custom data type that we can use elsewhere in our code. Enum values. We can create instances of each of the two variants of IP address kind like this. Note that the variants of the enum are namespaced under its identifier, and we use a double colon to separate the two. The reason this is useful is that now both types, address kind v4 and address kind v6, are of the same type, IP address kind. We can then, for instance, define a function that takes any IP address kind. And we can call this function with either variant. Using enums has even more advantages. Think more about our IP address type. At the moment, we don't have a way to store an actual IP address data. We only know what kind it is. Given that you've just learned about structs in Chapter 5, you might tackle this problem as shown in listing 6-1. Listing 6-1, storing the data and IP address kind variant of IP address using a struct. Here we've defined a struct IP address that has two fields, a kind field that is the type of IP address kind, the enum we defined previously, and an address type field of type string. We have two instances of this struct. The first, home, has the value of IP address kind 4, version 4, as its kind with associated address data of 127.0.0.1. The second instance, loopback, has the other variant of IP address kind as its kind value, version 6, and has an address 1 associated with it. We've used a struct to bundle the kind and the address values together. So now the variant is associated with the value. We can represent the same concept in a more concise way, just as enum, rather than an enum inside a struct, by putting data directly into each enum variant. This definition of the IP address says that both version 4 and version 6 variants have associated string values. We attach data to each variant of the enum directly, so there's no need for an extra struct. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 type IP address will always have 4 numeric components that will have values between 0 and 255. If we wanted to store version 4 addresses as 4U8 values but still express version 6 addresses as one string value, we wouldn't be able to with a struct. Enums handle this case with ease. We've shown several different ways to define data structures to store versions 4 and version 6 IP addresses. However, it turns out wanting to store IP addresses and encode which kinds they are is so common that the standard library has definitions we can use. Let's look at how the standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of two different structs, which are defined differently for each variant. This code illustrates that you can put any kind of data inside an enum variant, strings, numeric types, or structs, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. We'll talk more about bringing types into scope in Chapter 7. Let's look at another example of enum in listing 6-2. This one has a wide variety of types embedded in its variants. Listing 6-2, a message enum whose variant each store different amounts and data and types of values. This enum has 4 variants with different types: quit, has no data associated with it at all. Move includes an anonymous struct inside it. Write includes a single string. Change color includes three I32 values. Defining an enum with variants such as the ones in listing 6-2 is similar to defining different kinds of struct definitions, except the enum does not use the struct keyword and the variants are grouped together under the message type. The following structs could hold the same data that the preceding enum variants hold. But if we use different structs, which each have their own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6-2, which is a single type. There is one more similarity between enums and structs. Just as we're able to define methods on structs using impl, we're also able to define methods on enums. Here's a method named call that we could define on our message enum. The body of the method we use, self, to get the value that we called the method on. In this example, we've created a variable m that has the value message write string from hello, and that is what self will be in the body of the call method when m.call runs. Let's look at another enum in the standard library that is very common and useful, option. The option enum and its advantages over null values. In the previous section, we looked at how the IP address enum lets us use Rust type system to encode more information than just the data into our program. This section explores a case study of option, which is another enum defined by the standard library. This option type is used in many places because it encodes the very common scenario in which a value could be something or it could be nothing. Expressing this concept in terms of the type of system means the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Programming language design is often thought of in terms of which features you include. But the features you include are important too. Rust doesn't have a null feature that many other languages have. Null is a value that means there is no value there. In languages with null, variables can always be in one of two states, null or not null. In his 2009 presentation, Null References, The $1 Billion Mistake, Tony Hoare, the inventor of Null, has this to say. I call it my $1 billion mistake. At that time, I was designing the first comprehensive type system for the references in an object-oriented language. My goal was to ensure that all of the references should be absolutely safe, with checking performance automatically by the compiler, but I couldn't resist the temptation to put a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. The problem with null values is that if you try to use a null value as a not null value, you get an error of some kind. Because this null or not null property is pervasive, it's extremely easy to make this kind of error. However, the concept of null is trying to express However, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. The problem isn't really the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of a value being present or absent. This enum is option T, and it is defined by the standard library as follows. The option T enum is so useful that it's even included in the prelude. If you see, you don't need to bring it into scope explicitly. In addition, so are its variants. You can use some and none directly with the option prefix. The option T enum is still just a regular enum, and some T and none are still variants of type option T. The T syntax is a feature of Rust we haven't talked about yet. It's a generic type parameter, and we'll cover its generics in more detail in Chapter 10. For now, all you need to know is that T means that some variant of the option enum can hold one piece of data of any type. Here are some examples of using option values to hold number types and string types. If we use none rather than some, we need to tell Rust what type of option T we have. Because the compiler can't infer the type that the some variant will hold by looking only at a none value. When we have a some value, we know that a value is present and that the value is held within the sum. When we have a none value, in some sense it means the same thing as null. We don't have a valid value. So why is having option T any better than having null? In short, because option T and T, where T can be any type, are different types, the compiler won't let us use an option T value as if it were definitely a value type, a valid value. For example, this code won't compile because it's trying to add an I8 to an option I8. If we run this code, we get an error message like this. Intense. In fact, this error message means that Rust doesn't understand how to add an I8 and an option I8 because they're different types. When we have a value of a type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whatever type of value we're working with do we have to worry about possibility of not having a value. And the compiler will make sure that we handle that case before using the value. In other words, you have to convert an option T to a T before you can perform T operations with it. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is. Not having to worry about incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. Then, when you use that value, you are required to explicitly handle the case when that value is null. Everywhere that the value has a type is that isn't an option T, you can safely assume that that value isn't null. This was a deliberate design decision for Rust to limit nulls, pervasiveness, and increase the safety of Rust code. So, how do you get the T value out of some variant when you have the value of a type option T? So you can use that value. The option T enum has a large number of methods that are useful in a variety of situations. You can check them out in this documentation. Becoming familiar with the methods on option T will be extremely useful in your journey with Rust. In general, in order to use an option T value, you want to have code that will handle each variant. You want some code that will run only when you have some T value. And this code is allowed to use the inner T. Enter T. You want some other code to run if you have none value. And that code doesn't have a T value available. The match expression is a control flow construct that does just this when used with enums. It will run different code depending upon which variant of the enum it has, and that code can use the data inside the matching value. The match control flow operator. Rust has an extremely powerful control flow operator called match that allows you to compare a value against a series of patterns and then execute code based on which patterns matches. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different kinds of patterns and what they do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. Think of a match expression as being like a coin sorting machine. Coins slide down the track with various sized holes along it, and each coin falls through the first hole it encounters that it fits into. In the same way, values go through each pattern in a match, and at the first pattern the value fits, the value falls into the associated code block to be used during execution. Because we just mentioned coins, let's use them as an example using match. We can write a function that can take an unknown United States coin and in a similar way as a counting machine determine which coin it is and return its value in cents, as shown here in listing 6-3. Listing 6-3, an enum and match expression that has the variance of the enum as its patterns. Let's break down the match in the value underscore in underscore cents function. First, we list the match keywords followed by an expression, which in this case is the value coin. This seems very similar to an expression used with if, but there's a big difference. With if, the expression needs to return a Boolean value, but here it can be any type. The type of coin in this example is the coin enum that we defined on line 1. Next are the match arms. An arm has two parts, a pattern and some code. The first arm here has a pattern that is the value coin penny, and then the equals arrow operator that separates, actually that's equals greater than operator that separates the pattern and the code to run. The code in this case is just the value 1. Each arm is separated from the next with a comma. When the match expression executes, it compares the resulting value against the pattern of each arm in order. If a pattern matches the value, the code associated with the pattern is executed. If that pattern doesn't match the value, execution continues until the next arm. Much as a coin sorting machine, we can have as many arms as we need. In listing 6-3, our match has 4 arms. The code associated with each arm is an expression, and the resulting value of the expression in the matching arms is the value that gets returned for the entire match expression. Curly brackets typically aren't used if the match arm code is short, as it is in listing 6-3, where each arm just returns a value. If you want to run multiple lines of code in a match arm, you can use curly brackets. For example, the following code would print lucky penny every time the method called with a coin penny, but would still return the last value of the block 1. Patterns that bind to values. Another useful feature of match arms is that they can bind to other parts of values that match the pattern. This is how we can extract values out of enum variants. As an example, let's change one of our enum variants to hold data inside it. From 1999 through 2008, the United States minted quarters with different designs for each of the 50 states on one side. No other coins got state designs, so only quarters have this extra value. We can add this information to our enums by changing the quarter variant to include a U.S. state value stored inside, which we've done here in listing 6-4. Listing 6-4, a coin enum in which the quarter variant also holds U.S. state value. Let's imagine that a friend of ours is trying to collect all 50 state quarters. While we sort our loose change by coin type, we'll also call out the name of the states associated with each quarter, so if it's one our friend doesn't have, they can add it to their collection. In the match expression for this code, we add a variable called state to the pattern that matches the value of the variant, coin quarter. When a coin quarter matches the state variable, we'll bind that to the value of that quarter state. Then we can use state in the code for that arm like so. If we were to call value underscore in underscore cents coin quarter U.S. state Alaska, coin would be called coin quarter U.S. state Alaska. When we compare the value of each of the match arms, none of them match until we reach coin quarter state. At that point, the binding for state will be the value of U.S. state Alaska. And then, we can then use that binding in the print line expression, thus getting the interstate value out of the coin enum variant for quarter. Matching with option T. In the previous section, we wanted to get the inner T value out of some case when using option T. We can also handle option T using match as we did with the coin enum. Instead of comparing coins, we'll compare variants of option T. But the way that the match expression works remains the same. Let's say we want to write a function that takes an option I32, and if there's a value inside, adds 1 to that value. If there isn't a value inside, the function should return the none value and not attempt to perform any operations. This function is very easy to write thanks to match and will look something like listing 6-5. Listing 6-5, a function that uses a match expression on an option I32. Let's examine the first execution of plus underscore 1 in more detail. When we call plus underscore 1 5, the variable x in the body of plus underscore 1 will have the value of sum 5. We then compare that against each match arm. None equals greater than none. The sum 5 value doesn't match the pattern, none, so we continue to the next arm. Sum I equals greater than sum I plus 1. Does sum 5 match sum I? Why, yes it does. We have the same variant. The I binds to the value contained in sum, so I takes the value of 5. The code in the match arm is then executed, so we add a 1 to the value of I and create a new sum value with our total 6 inside. Now let's consider the second call of plus underscore 1 in listing 6-5, where x is none. We enter the match and compare to the first arm. It matches. There's no value to add to. So the program stops and returns the none value on the right side of the equals greater sign. Because the first arm matched, no other arms are compared. Combining match and enums is useful in many situations. You'll see this pattern a lot in Rust code. Match against an enum, bind a variable to the data inside, and then execute the code based on it. It's a bit tricky at first, but once you get used to it, you'll wish you had it in all languages. It's consistently a user favorite. It's constantly a user favorite. Matches are exhaustive. There's another aspect of match we need to discuss. Consider this version of our plus underscore 1 function that has a bug and won't compile. We didn't handle the none case, so this code will cause a bug. Luckily, it's a bug Rust knows how to catch. If we try to compile this code, we'll get an error. Rust knows that we didn't cover every possible case and even knows which pattern we forgot. Matches in Rust are exhaustive. We must exhaust every last opportunity in order for the code to be valid, especially in the case of option T. When Rust prevents us from forgetting to explicitly handle the none case, it protects us from assuming that we have a value when we might have null, thus making the billion-dollar mistake discussed earlier. The underscore placeholder. Rust also has a pattern we can use when we don't want to list all possible values. For example, a U8 can have valid values 0 through 255. If we care about the values 1, 2, 3, 5, and 7, we don't want to have to list out 0, 2, 4, 6, 8, 9, all the way up to 255. Fortunately, we don't have to. We can use the special pattern underscore instead. The underscore pattern will match any value by putting it after our other arms. The underscore will match all possible cases that aren't specified before it. The colons is just the unit value, so nothing will happen in the underscore case. As a result, we can say that we want to do nothing for all the possible values that we don't list before the underscore placeholder. However, the match expression can be a bit wordy in a situation in which we care only about only one of the cases. For this situation, Rust provides if let. Concise control with if let. The if let syntax lets you combine if and let into a less verbose way to handle values that match one pattern while ignoring the result. Ignoring the rest. Consider the program in listing 6-6 that match an option U8 value but only wants to execute code if the value is 3. Listing 6-6, a match that only cares about executing code when the value is sum 3. We want to do something with the sum 3 match, but do nothing with any other sum U8 value or the none value. To satisfy the match expression, we have to add underscore equals greater than colons after processing just one variant, which is a lot of boilerplate code to add. Instead, we could write this in a shorter way using if let. The following code behaves the same as the match in listing 6-6. The syntax if let takes a pattern that an expression separated by an equal sign, and it works the same way as match, where the expression is given to match and the pattern is its first arm. Using if at means less typing, less indentation, and less boilerplate code. However, you lose the exhaustive checking that match enforces. Choosing between match and if let depends on what you're doing in your particular situation and whether gaining conciseness is an appropriate trade-off for losing exhaustive checking. In other words, you can think of if let as syntax sugar for match that runs code when the value matches one pattern and then ignores all other values. We can include an else with an if let. The block code that goes with the else is the same as the block code that would go with the underscore case in the match expression that is equivalent to the if let and else. Recall the coin enum definition in listing 6-4, where the quarter variant also held a US state value. If we want to count all the non-quarter coins we see while announcing the state of the quarters, we could do that with a match expression like this. Or we could use an if let and else expression like this. If you have a situation in which your program has logic that is too verbose to express using a match, remember that if let is your Rust toolbox as well. Is in your Rust toolbox as well. Summary. We've now covered how to use enums to create custom types that can be one of a set of enumerated values. We've shown how the standard library option T type helps you to use type system to prevent errors. When enum values have data inside them, you can use match or if let to extract and use those values. depending on how many cases you need to handle. Your Rust programs can now express concepts in your design using structs and enums. Creating custom types to use in your API ensures type safety. The compiler will make certain your functions get only the values of the type each function expects. In order to provide a well-organized API to your users that is straightforward to use and only exposes exactly what your users will need, let's now turn to Rust modules. Okay, that's the end of chapter 6. The next chapter, chapter 7, managing growing projects with packages, crates, and modules. Okay, there we go.